We're going to look at adding and subtracting half-cell reactions, and then get to one of my favorite things, which is the Nernst equation. All right, so some of you may have encountered this problem on the problem set already. Suppose you need to know a standard reduction potential, and it's not given to you in the back of the book. But other things are given to you in the back of the book. Can you calculate the thing you need from related equations? So suppose you really want to know the couple, the reduction couple for copper 2 going to copper 1, but that's not given. You find copper 2 with 2 electrons going to copper 0, and you find copper 0 going to copper plus 1 with 1 electron, and you'll realize that if you combine these equations, you'll get the desired one. So if you add these together, you have copper 2 with 1 electron cancels out here, the copper solids cancel out, and you're left with copper plus 1. So you add these together, and you know the potentials for these, how do you get the standard potential for the thing that you've come up with, for the sum of those? So as someone actually asked me after class, or before class, you have to go to back to free energy, and you do, but I'm going to drive an equation so that you don't have to go all the way back. But this is, in fact, how you do the problem. You think about the different free energies. So the new reaction, the sum, the new delta G for that new reaction will be equal to the delta G naught for the reduction minus the oxidation reaction here. But we can substitute for delta G this minus n Faraday's constant times our reduction potential and put it in to this equation here. And so we have it for the new reaction and then the two reactions that we're adding together. So we have Faraday's constant in common, so that's going to cancel out. And we can also move N3 to the other side because we want to solve for this new E value, this new standard reduction potential. And so that's going to be equal to the number of moles that are involved in the reaction that's the reduction times its reduction potential minus the number of moles involved in the oxidation reaction with its reduction potential, and then the number of moles for the reaction that's the new reaction in question. So we can use then this equation to look for a half-cell reaction that is a sum of two other reactions. So let's go and use that equation then. So here we have the known values. We know the couple for copper 2 to copper 0. We know the couple for copper 1 to copper solid. And this is what we want to know. So we can use this equation. Which of these reactions is the reduction? What value am I going to put in here? Which of these goes into the reduction? Which of these is a reduction reaction? Yeah. And how many moles of electrons are involved? Yeah. So we put in 2 times 0.340 volts. And then over here in the oxidation, there's 1 electron involved, and we put in our other potential. So 1 times 0.522. And what are the number of moles of electrons for our desired final reaction? 1. And so then we can do the math and come up with an answer of 0.158 volts. And so now we've just come up with a new reduction potential. We've calculated a new reduction potential for this half-cell reaction right here. So this equation will be given to you on an exam, and all you need to do is know how to use it. So we've calculated now the standard reduction potential for copper 2 to copper plus 1. So just a little note about when you're going to use this and when you're going to use the other equation that I showed you. So if we're talking about a whole electrochemical cell, the number of moles that are released at the anode are going to equal the number of moles taken up at the cathode and be the number of moles involved in the overall equation. So this equation is not necessary. And for a full electrochemical cell, we're going to use the equation that I gave you before for this delta E naught for the cell. So we just use this. But if it's not a whole electrochemical cell you're talking about, if you're talking about calculating a half cell potential, then you need to use this equation. Both of these equations will be given to you on sheets for the exam. This one's for an electrochemical cell. This one's for calculating a half cell potential. So again, if it's a half cell potential, you want to use this equation. OK, so now the Nernst equation. So some of you may have encountered